We are doing Oxford on Mars. My name is Omer lIchter. I come from Israel.
My name is Konstantinos Chiotis. I come from Cyprus, pretty close to here.
I'm Shoham, Atia, and I come from Israel as well.
So, as many of you may know, humans for a long time have been dreaming of going to Mars, exploring Mars, and also getting to live there. In addition, there are many, many things that are set in the future to go there, and maybe even to replace, to move from Earth to Mars as a new, as our resources go down in Earth.
As much as it doesn't concern us now, this will be a great. This will be the future. We also have so many visionaries working on this 24/7. For example, Elon Musk. There's a cool quote he said.
Sorry for the technical difficulty. So what now? What are the needs to survive? What do humans need to survive? Where can we get everything that we need? The water, the oxygen, the food, the fuel. How can we sustain ourselves?
The best way is not to think to transport it from Earth, because it's not efficient and it wouldn't really work for long periods of time if we want to actually live on Mars. So we try looking at what Mars offers, what its terrain, what's inside its core, and thankfully, recently NASA has found that there's water ice on the poles and around it. So we can use that for our benefit.
So harvesting ice. We can harvest ice using an autonomous rover that locates the ice using a hydrogen spectrometer. It's self-sustainable, and it uses a drill for the ice extraction. It turns the ice into a liquid in a device, in a concave device.
So the rover itself, it's as Omer said, it's autonomous, it's self-charging, it's programmed itself to go from its base, harvest the ice, put it in a special tank, convert it into liquid, and bring it back and charge again. So you don't need to do anything. It's lightweight, it's made of carbon fiber, and that's it. Here you can see a very specific representation of the rover. These are the tanks that harvest the sunlight to turn the ice into liquid. This is a dog. This kind of represents like the home base. And this is a drill, which here you have a hollow drill bit, which drills into the ice and makes perfect ice rods that are placed inside the tanks. The tank itself, you might be thinking, what does this conversion tank do? It uses special concave lenses around it to take the sunlight and put it in a single focal point, so you can melt the ice. Here you can see the next section of the tank. So we get the sunlight. Here are the concave lenses, which shape the sunlight. On the inside there are two mirrors connected to each other with a slit in the middle. So from wherever you get sunlight, you don't have a problem. So you don't have to turn it yourself, because yes, you get light from everywhere, but then it hits those mirrors, it reflects, and at any point and instance, if you have sunlight in any way, you will have a focal point in the mirror in the middle to melt the ice. So these tanks are fabricated by carbon fiber and the optic materials. They're very light. They're 3.6 kilograms, and they're very compact too. They have a length of 35 centimeters and a radius of 7 centimeters. So the water inside, as I said, the rods lie inside and they melt. The heat increases the temperature so much that it turns to water. And this process also happens the return of the rover. So while it's returning, it harvests sunlight and it melts.
So actually, well, the autonomous rover is going automatically, as we said, to collect the ice. Then it comes back to the home base and charge automatically, and transfers the liquid water into tanks inside the home base, and also it charges by flexible solar panels, light-weighted solar panels. In order to use the water for what we want to use them, we use electrolysis, which give us oxygen and hydrogen. So what can we do with hydrogen? Oxygen, sorry. What can we do with oxygen? Oxygen is a very vital thing for human survival, and we get it from the reaction. We know the average human consumes around 1,000 liters of oxygen. And in order to have this amount of oxygen, we need around 1.5 kilograms of ice water. Hydrogen. From the hydrogen, we can use hydrogen for many things. One of the uses of hydrogen is making energy, which also is something that we need on space. So we take the hydrogen and we use it in many ways. One of them is this reaction, but the problem with this reaction is that it requires oxygen. So where do we get oxygen from?
So why do we electrolyze the water? Somebody could say, well, you have water, you have one of the most vital things to human beings. Why make it into something else? Because water is also something we need. We get water from waste. So it's already solved by NASA. It's been used in the ISS for years now. So why solve a solution, break a solution to solve another problem? So the biggest problem right now is oxygen, because how are you going to transfer it from Earth, and where are you going to find it? So to us, this is the best solution, to have oxygen for a long period of time for sustainable and efficient living on Mars.
So we had a problem before. We had hydrogen and we didn't know how to use it to create energy. So we thought about a technology called fuel cell. Fuel cell takes the oxygen and takes hydrogen and creates energy. How do we get the oxygen? We increase the amount of ice water we take by doubling it, and then we have enough oxygen and hydrogen to create energy and supply oxygen for human needs.
As you can see from the dialysis, we get the oxygen and we get the hydrogen. So part of the oxygen we are using for breathing, and the other part we're using with the hydrogen to get its fuel cells, that we can get from that energy to power whatever we need.
So all in all, this project is it's something to think about. What are we going to do in 20, 30 years? Where are we going to be for space exploration? And this is something that will change, not revolutionize, but change the way we think about living in space. Most of us think, oh, we have to take what we need to that place, but if we search enough, we can find alternative solutions that could actually work. So there's that, and that's something to think about. Maybe someday I'll become an astronaut. Thank you very much.
What are the temperatures on Mars?
So the average temperature in Mars, it's minus 61 degrees average for every season and all. But in the summer, it gets up to 271 degrees Celsius. But because we're close to the ice caps, that temperature is decreased in a big amount.
So you get, the question would be the pressure as well. Do you get water boiling or melting check that it matches with water properties, physical properties?
Well, when you have the tank and it actually takes the water to a liquid state. If you have a coating on top to kind of regulate how much sunlight you get, so you can know at that instance for the time the chip is going to need for it to boil, I can have a coating on top that will give me exactly the amount of sunlight I need to turn into water and not vapor.
Is it just temperature that you need to control?
And pressure also. So, for instance, there could be regulator valves that could also release maybe the extra gases that would be inside, but not compromise the water. And that's why we have the tanks on a flat surface, so on top we could have regulators to...
Is there enough sun radiation on Mars for cubic?
Yes, there is, because from what we have calculated, for this device, you could have 590 watts per meter square. So there is enough radiation. And also, Mars doesn't have a very sufficient atmosphere, neither. 590 watts per meter square.
And how much is it on Earth? It's maximum 1,000 watt. So I doubt it is more than half on Mars, let alone the fact that you are near the poles, and therefore the amount of solar radiation is much smaller per unit area. It's on Earth. It's 1,000 watt per square meter at maximum.
So, to get the sufficient sunlight on the summer days, the polar ice caps actually have sunlight. The summer, they actually have a lot of sunlight, and sometimes they even vaporize. But that's not the case here. So you could have sufficient sunlight to...
How big should the collector be?
The collector, for now, this project is based around the Mars rover that exists, those sizes. Actual tank, as I said, first around 35 centimeters long, and the radius of 7 centimeters, 35 centimeters long and 7 centimeters radius. But this can be applied to a bigger extent. You can apply it to future missions to a way larger extent for larger amounts of ice, water, integrate water, and all that.
I have one more question. Part of the electrolysis that you apply is in order to produce oxygen, which will be used later on for burning the hydrogen. Is that correct?
Yeah. Not burning, using fuel cells.
Well, okay. Producing energy.
Yeah.
Okay. That's a question.